For years, we've kind of been sold this idea that quantum machine learning is this impossibly complex beast, right? Something that needs perfect hardware and just ages of training to get it under control. But what if the smartest move isn't to try and tame the beast at all, but to just let it run wild? Well, that's exactly what we're digging into today. We're talking about something called quantum extreme learning machines, a pretty radical idea that says, hey, let's just skip the hardest part of AI entirely to unlock a totally new kind of power. All right, let's get into it.
So, here's how we're going to break it down. We'll start with the big idea behind this quantum shortcut. Then we'll dive into the nuts and bolts of how these things actually work. Of course, we'll also face the tough hurdles they need to clear before looking at how they're already popping up everywhere from physics labs to industrial elevators. And finally, we'll look ahead to the hybrid future, where this tech just might become a tool for every developer out there.
Okay, Section 1, a quantum shortcut for AI. This is all about a surprisingly simple philosophy, really. Why bother with the most difficult, most expensive part of machine learning if you don't have to?
I mean, think about it. Most quantum machine learning models are like these brilliant but incredibly stubborn students. Training them it's a slow, grueling process. They often run smack into something called a barren plateau, which is basically where they just stop learning, no matter how much data you feed them. It's the biggest bottleneck in the whole field. So the question becomes, what if we just skipped it?
And this is the elegant, honestly kind of gutsy solution that quantum extreme learning machines, or QELMs, bring to the table. The whole philosophy is really this. Just let the quantum system do its thing. Let it be mind-bogglingly complex. Don't even try to train it or tune it. Instead, you just use its natural, fixed state as this incredibly powerful processor. The only bit you train? A super simple classical layer right at the end to make sense of the results. So you get all this amazing quantum power, but you completely sidestep the nightmare of quantum training. It's brilliant, really.
Now, what's so cool about this is that this shortcut isn't some brand new idea that came out of nowhere. It's an evolution, an idea that was just waiting for the hardware to catch up. It all started in the classical world, way back in 2004, with this idea that maybe, just maybe, the hidden layers of a neural net don't need all that painful training. It wasn't until 2017, when quantum hardware started to mature, that researchers had this light bulb moment. A quantum system is the ultimate untrained hidden layer. And from there, things just took off. By 2022, you see the first patents, and by 2026, we start getting these major hardware demos at a real utility scale, proving this whole shortcut idea actually works.
Okay, let's move on to Section 2 and see how this all fits together. We're going to go inside the engine here and really understand the mechanics of how these QLMs process information.
It pretty much all boils down to a simple three-step pipeline. First, you encode. You take your classical data, let's say the pixels of an image, and you map them into the quantum state of your qubits. Second, and this is really the magic step, you evolve. You just let that state run through a fixed, completely untrained quantum system we call a quantum reservoir. This scrambles the data, blasting it into this unbelievably vast computational space. And finally, you read out. You just measure the result and use a dead simple classical model to figure out what it means. No backpropagation, no gradient descent, just pure, raw quantum dynamics. So the whole thing really hinges on understanding this quantum reservoir. I think the best way to picture it is like a computational rock tumbler. You throw in your data, which is like a big jumble of different rocks. The reservoir, which is literally just the quantum computer hardware itself running a fixed program, tumbles and scrambles all that data. And in the process, the hidden patterns in your data start to separate out, making them super easy for a simple classical model to spot on the other side. It's this powerful nonlinear transformer that needs exactly zero training. Now, you might have heard of a cousin to this idea, something called quantum reservoir computing, or QRC. And the key difference, which really shows off the architecture here, is memory. A QALM is memoryless. It looks at each piece of data, like one single image, completely on its own. A QRC, on the other hand, has memory. Its current state actually depends on what it saw before, which makes it perfect for things like time series data, financial markets or weather forecasts. It's a subtle but really crucial difference in their design.
Okay, so this all sounds pretty amazing, I know. But it's not a total free lunch. There are definitely challenges. So let's move to Section 3 and talk about the biggest hurdles QLMs are facing as we try to scale them up. The big one is what people in the field are calling the vanishing signal problem.
The technical name for this roadblock is exponential concentration. And yeah, it's just as scary as it sounds. This is the main ghost in the machine that researchers are trying to exorcise right now.
So what is it? Well, basically, as you add more and more qubits to make your reservoir more powerful, something really weird starts to happen. The answers you get out for different inputs all start to look the same. They concentrate around one single average number. So the unique fingerprint of your input data just gets completely washed away, erasing the very information you were trying to process in the first place. It's kind of like the QELM version of a barren plateau, a total signal-to-noise nightmare.
And it turns out there are a few key culprits behind this signal loss. For one, too much entanglement, which we usually think of as a quantum superpower, can actually smear all the data signatures together. Then you've got real-world hardware noise, which is constantly trying to push the quantum state toward this bland, useless average state. And finally, even the way you measure the system matters. If you measure a ton of qubits all at once, you can actually make the problem worse. It's a really delicate balancing act.
But hey, despite all those challenges, the progress has been undeniable. So for Section 4, let's switch gears from theory to the tangible, real-world results that are starting to pop up. We're taking this tech out of the lab and putting it to work.
How's this for tangible? 13,000 times. Yeah, in 2025, Google ran an experiment called Quantum Echoes that used a QLM-like process, and it achieved a 13,000-fold speed-up over one of the world's fastest supercomputers. Now, to be fair, it was for a super-specific physics task, but it was the first time anyone proved that a real, verifiable quantum advantage was possible with this kind of setup.
Then, not long after, in early 2026, IBM just raised the bar on scale. They ran a QLM on a 124-qubit processor, one of the largest quantum machine learning demos ever. And what they showed was that even at this massive scale, which is basically impossible to simulate with a classical computer, the QLM approach was still robust and gave them meaningful results, even on the noisy hardware we have today.
Okay, but let's get even more practical. An industrial company called Arona used a QLM to optimize elevator scheduling, predicting passenger wait times. And it worked. It actually required fewer data points than their classical models. But, and this is a big but, this quote is such a fantastic reality check. When they moved from their perfect simulation to a real, noisy quantum computer, the performance dropped by 250%. It just perfectly highlights both the incredible potential and the very real hate you take from today's hardware limitations.
And you better believe the financial markets have noticed. This is not just some academic game anymore. I mean, look at these numbers from 2025. Rigetti, whose hardware gets used for this kind of research, saw a mind-blowing 5,700% gain. Companies like D-Wave and IonQ saw massive growth too. What this tells you is that investors are betting big that the companies building the hardware for these shortcuts are definitely on the right track.
And that brings us to our final section, the hybrid quantum future. This is all about what's coming next. And spoiler alert, it's all about integration. This is the moment where this powerful quantum technique stops being a niche science project and starts becoming a tool that people can actually use. So the big philosophical shift that's happening right now is this move away from using the quantum reservoir as just a random black box. In the past, the idea was, hey, let's just use any chaotic quantum system we can find and hope for the best. The future, though, is all about interpretable dynamics. It's about carefully engineering the reservoir, tailoring its physics to perfectly match the structure of the data you're trying to analyze. We're moving from a black box we don't understand to a gray box that is actually designed for the job.
And this is the end game. This is where it's all headed. See, the goal isn't for every software developer to suddenly become a quantum physicist. No way. Instead, QLMs are being packaged into software frameworks, basically becoming feature-boosting plugins. So a Python developer working on a totally normal AI problem will soon be able to make a simple API call to a quantum computer to generate these unbelievably powerful features, and then just feed those right back into their normal workflow. It is the ultimate hybrid convergence.
And look, this isn't just a theory. It is happening right now, with serious money pouring in. IBM Ventures, for instance, is backing startups like SQK, which is using these hybrid algorithms to completely change healthcare diagnostics with clearer medical image reconstruction. We're talking better, faster MRIs. They're also funding companies like Codex Quantum, who are building these quantum-native analytics platforms for big business. From drug discovery to modeling complex financial systems, this is where the commercial rubber really meets the road, proving the real-world value of these quantum shortcuts.
So when you boil it all down, the quantum revolution we've all been waiting for, it's probably not going to be a single dramatic moment of quantum supremacy. It's far more likely to be a series of these pragmatic, clever shortcuts, just like the quantum extreme learning machine, hybrid solutions that give us a real, concrete advantage on specific, high-value problems today.
The only question left, really, is which industry is going to be the first to truly get it and take that first shortcut into the future?